Good afternoon or good morning for those that are in different time zones. Welcome to this Discover Us webinar. It is a series of webinars organized by the Discover Us project, which aims at fostering the collaboration between Europe and US in topics of distributed computing, swarm intelligence. It's the digital continuum in general, okay? So today we have the honor that we have Ewa Deelman, who's a very good, very well-known person, at least in my area of research. Ewa is the research director at the University of Southern California of the Information Science Institute and has been leading the Pegasus project for many years now, which is one of the leading workflow management software in the world. So Ewa, I don't want to take more minutes from your talk. Whenever you want, you can start. Thank you.
Thank you so much, Rosa, and I really appreciate the invitation to give a webinar here. What I would like to talk about is a new project called SWARM, that stands for Scientific Workflow Applications on Resilient Systems. It is part of a resilience systems program within the US Department of Energy. And it's basically a program that looks at how we can build next generation systems to be more resilient than what we have today. And in this work, we're particularly focusing on scientific workflows and scientific applications. As I mentioned, this is a relatively new project. We're starting our second year. So a lot of the work here that you'll see is underway. And so I have some initial results to share. But this is not a completed project. So I also think this is a good opportunity for us to see where the potential collaborations between the EU and US. So this project involves a number of team members. We have 6 institutions, and we have the expertise of folks that do research in AI, in resource provisioning, in networks, in mathematical modeling, resilience, and many others. So we're putting our heads together to think about how we can build these resilient systems of the future. Before I talk about this particular project, I also want to put it into context and talk about traditional workflow management systems and some of the issues that we face in that domain, and motivate why we're looking at this new way of doing workflow management. So I've been working on the Pegasus workflow management system since about 2001. And at that time, we're looking at a number of different applications that we're trying to support, particularly executing in distributed environments. So the challenges that we saw across application domains was that the scientists wanted to describe the complex workflows in a simple way. They wanted to have the workflows run across distributed and heterogeneous resources, and heterogeneous both in terms of data and the resources themselves. Also, they needed to deal with resources and software that changes over time. So basically, new machines come online, they need to still be able to run the same type of analysis that they've done before. And obviously, ease of use, ability to monitor and debug large workflows was also a challenge. So our focus based on this, working with these various domains was to focus on the separation between the workflow description and the workflow execution, so that the workflow description is resource independent, and then it's the job of a workflow management system to plan the execution of the workflow onto the resources and to schedule the individual tasks in a way that's scalable and performant. Then after the planning, when the execution takes place, we need to be able to monitor the task, detect any errors, and recover from them. If we cannot recover from the errors, then the user would need to have help debugging the system, since the workflows can be quite large and the environment quite heterogeneous, and so provide various interfaces to do that. And then finally, we also saw over the years that the workflows as they are designed by the scientists are not necessarily optimized for a particular platform, or they have particular challenges in terms of scalability. So over the years, we also been developing various workflow optimization techniques to restructure the workflow for performance and fault tolerance. So from this graphic, I think the main point to take is that Pegasus has this notion of a submit host from where the jobs are being sent to execution hosts. We have a compute sites that can be multiple to where the execution will take place. The data is also can be at different locations, and the data can be pulled in to the site if it's remote, or we also can have things collocated so that on an HPC system, for example, the storage is collocated with the compute site. In a cloud environment, this is more distributed, but with this model, we can basically compose, in some sense, environments on which Pegasus can execute the workflows. And so some of the applications that have been using Pegasus, LIGO has been using it since the very beginning. This is a gravitational wave detection observatory that in 2016 confirmed the first ever direct detection of gravitational waves. And the workflows are mostly high throughput computing workflows. They access terabytes of data. They take data from multiple detectors, and they use both the LIGO high throughput computing infrastructure and also the US national resources to do the computations. So with this work, actually, the LIGO scientists have received the Nobel Prize in 2017. Another project that we've been involved with since 2005 is the Southern California Earthquake Center. Now it's called the Statewide California Earthquake Center, and the scientists have been running workflows to calculate the seismic hazard maps, first of Southern California and now also of Northern California as well. And so these are the numbers fresh off the press. The scientists just finished the last science run that took about 45 days of computing, during which they had 24/7 operations. So this is, again, shows you, where the automation and power of Pegasus comes in. It can manage these type of computations. There are about 945 workflows with over almost 28,000 jobs, and these are mostly MPI jobs. They were executed on Frontier. So this is the exascale machine at Oak Ridge National Lab, and there they used about 55,000 node hours. And the GPU calculations were done on Frontier. Then the CPU post-processing and other calculations were done on Frontier, and Pegasus moved the data between the two infrastructures, about 330 terabytes of data automatically moved between the computations. And there it took 125,000 node hours. So we didn't have, or the scientists didn't have any special reservations or priority bumps, that were able to use 44% of Frontier at times and 12% of Frontera to do the computations. The data within these workflows was 1 petabyte, and 9 million different files were transferred again automatically to SCEC resources at USC. So you can see these are very large-scale applications that can leverage modern infrastructures, but we also use Pegasus, 15 years ago to run on different HPC systems, and we need to be able to keep up with this. The other applications that we see coming online right now are applications that made use of both edge and cloud resources. So this is an application from weather modeling, where the scientists have Doppler radars deployed in the Dallas-Fort Worth area. They do some calculations projecting weather events at the radars at the edge. However, when there are severe storms that come through the area, then you need to offload some of the computations to the cloud to be able to run a variety of different scenarios quite quickly. So again, the model of separation of compute and execution, and also compute and data, and also the workflow description from the workflow execution helps us to quickly run workflows across different infrastructures. So what's the issue of from this? So you can see we can run on HPC systems, on high throughput computing resources at the edge. And so the problem is that the limitations come from the single point of failure, where the workflow management system manages the execution of a workflow across these various resources. So even if you have HPC systems, and not too many of them, if the workflow management system goes down, then the computations are going to grind to a halt. You can put in strategies for resilience. However, they're often static, and they also require operators and system operators and designers to put a lot of effort in making rules of how to respond to various conditions. So altogether, the system adaptivity is limited and it's brittle. At the same time, we also see many more different types of systems coming online and being available across the network. So especially with cheap IoT devices that have transient connectivity, they themselves can be very prone to failures, and they need management and coordination. So we see that we need different types of approaches to do resource management. So in our Swarm project, we look at designing novel and resilient and performant execution platforms where we can manage the workflows across a variety of different heterogeneous resources. This will empower researchers to reach their scientific pursuits in an efficient manner, so reaching for new applications that make use of edge resources and IoT devices and can run across the computing continuum. And we want to improve the execution of on-demand jobs for these workflows that span multiple facilities and heterogeneous systems. So our hypothesis in this work is that to achieve resilience and resilient workflow execution, we can use decentralized fault tolerance adaptation strategies that are inspired by swarm intelligence techniques, and also advances that are happening now in machine learning and high performance computing. So as a result of building systems that are based on swarm intelligence, we think we can build systems that are more robust, scalable, and flexible. So we are reimagining the way workflow management systems will work in the future. We're thinking that users and also instruments and other agents can place jobs in a common resource pool. And obviously you can think of, well, maybe that's not very resilient, but the technologies for doing distributed data management has come a long way. So we're leveraging that in this work and potentially extend in that direction. But here we are assuming that we have this distributed infrastructure where the jobs and workflows come in. From this global pool, we have agents picking off jobs that are appropriate for the infrastructure and executing these jobs on the resources. It's also possible that we have multiple levels of agents. So we have agents that represent an HPC system, for example, or a facility which has HPC, cloud, and other resources. So the agent picks up the workload that's appropriate for that facility, and then agents within the facility can also pick off jobs that are appropriate for them. So in the system, why we're using swarm intelligence? Well, it has nice properties of decentralized coordination. So you can interact locally with your environment and achieve collective behavior. It has self-monitoring and self-healing, and it has obviously it draws inspiration from nature and shows this kind of very decentralized approach to providing solutions and resilience. So, however, there are challenges to using swarm intelligence for this type of work, or in general, the consensus between swarm agents can be slow, so that decision-making can be slow as well. They have also limited perception because they're looking primarily in their own environment, so they're difficult to optimize. There are also network challenges. So if the networks go down, it can also the effectiveness of collaboration and can be a challenge. So you need to be able to use protocols that take that into consideration. And sometimes the cooperation is suboptimal as well. So you might have subpar outcomes. However, we can overcome some of these challenges, and that's what we propose for Swarm. So we want to infuse traditional scheduling algorithms into the Swarm agents, so they are aware of the type of conventional methods that are available for scheduling. We want to also infuse them with machine learning techniques, so they become more powerful. And we also want to ensure that these agents have autonomy that is provided by innovative AI techniques, so we can promote better self-monitoring, self-diagnosis, and self-healing. And sometimes we can also, because we do have HPC resources in the mix, we can also leverage these HPC resources to build more complex swarm intelligence algorithms. So in that context, this is, again, if you looked at we saw the picture of a global job pool, so we can imagine it, again, as this dynamic job pool where the jobs are submitted to the system. And so this is a high-level model of what we're pursuing right now. And then we have agents that communicate with each other and then pick off jobs from the dynamic pool. They make decisions about which workflows or job to select for the execution. So you can imagine that this will be your high-performance, your research computing facility. It has a variety of systems. It can have HPC systems, a cloud system. It may be a quantum computer, so it picks up jobs that are appropriate for that system and puts it in the local job pool for that resource. From there, the different resource agents, could be the HPC system or others, pick up the jobs that they want to and can execute on the resources. So here the decisions are really, once the agent picks up a job for resources, how to schedule which resources to use for the job. And throughout these decisions, we also propagate the fault information about the resources up the chain so that that's taken into consideration when making decisions. So our general methodology in Swarm is to first decompose a problem into job selection. So job selection from the high-level pool, and right now job scheduling at the lower level. So this is more of a centralized approach where once a job is assigned to a particular facility, the scheduling can take place there. We're looking at consensus algorithms that allow the Swarm to a way to decide of which jobs each of the agents can pick off. And we're also looking at overlay networks, so how to make this consensus algorithms more efficient, so through better communications. And then we also are working on a mathematical formulation of a problem, but the evaluations we're planning to do are primarily through simulation, through emulations on a variety of test beds, and also through system prototyping in the future. So I'm going to be talking about each of these approaches, where we are with them right now, and how we are evaluating them. So the first part of the work I would like to describe, this is led out of RENSI by Anirban Mandal, is the consensus algorithms. So here we're looking at job selection. So this is from the high-level pool, how the agents are selecting jobs for execution. So they need to use a consensus algorithm, so to decide among themselves who's going to be executing which jobs. And obviously, when you designing these algorithms, you need to balance fault tolerance, flexibility, and scalability. So we looked at existing consensus algorithms, so BBFT, which is the practical Byzantine fault tolerant algorithm, which is quite flexible, but doesn't scale well. We have RAFT that scales better, but it also has centralized components and doesn't allow for dynamic agent topologies. And there are also more complex algorithms, Paxos, which we think has too strong too high of a complexity for our purposes, as is the POW, which power of work, which also is a proof of work, which also is a very resource intensive. So again, not very appropriate in our environment. So the goal is to find a more efficient, scalable consensus mechanisms that's suited to our swarm agents. And with our first solution is to look at adapting PBFT to make it a greedy consensus algorithm, where basically each agent manages the various resources that could be CPU, RAM, disks, and GPUs. They select the jobs from the pool, and they select the job based on minimizing the execution cost. And this is a very simple job selection because in this work, we focus on the consensus rather than the mechanism of selection. So we basically, the agent estimates the feasibility of each job based on resources that they have available. And if it is feasible and the projected it calculates the current load and the feasibility times the projected load. And then if it's minimal across other systems, then it bids on that particular work. And if it's not feasible, it's infinite. So in this consensus algorithm, so all the agents communicate with each other, and this is something that we address in the next segment of the talk. And the consensus is achieved through 3 stages. So the pre-prepare, where an agent proposes a job selection, prepare where other agents validate and acknowledge this proposal, and then commit where there is a quorum of confirmation to finalize the decision. And so we evaluated this particular algorithm through emulation. So we use a fabric testbed in the US. So this is a testbed that focuses primarily on network behavior. So we can set up various network topologies, which are appropriate for the evaluation of consensus algorithms that depend on network communications. We use Kafka for low latency communications and between the agents. So this is an example of setting up a swarm of 5 agents on Fabric. So the evaluation metrics that we use have a scheduling latency, which is defined as the total time a job remains in the job pool before it being selected for consensus. Sorry, and it includes the time to reach the consensus as well. And the idle times it's the time that the agents remain idle with no jobs to process. And then we have various variations on this algorithm, which is in the single case, the algorithm picks off 1 job at a time. In the multiple case, it picks multiple jobs, and we evaluate it with 3 jobs at a time to do the selection of the resources where to execute. And so we did the comparison of the various protocols, in particular Raft, that you see in blue right here. And we have the task index. So here we have 10 tasks running across, across the agents. And this is the scheduling latency. So how long it takes for the jobs to be picked off from the pool. So Raft performs best, but however, as I mentioned before, it has centralized components, and it also lacks this dynamic membership functionality. So if agents cannot come and go in this kind of protocol, PPFD, you see in orange, has quite a high variability in the scheduling latency. Swarm single has also this type of behavior. So it seems in this case, it looks like basically in the PBFT, there's a lot of conflicts in the protocol because the jobs are selected independently. Whereas from single, the job, there's faster consensus because each agent calculates the cost for everybody else as well. But the calculation offsets the benefit from the faster consensus. And then in multi, This seems to be the best in this particular case. So we picking up 3 jobs at a time really gives you better scheduling latency. So future work in this particular area of the project is to look at scaling. So how can we scale the problems and potentially adjust the algorithms, and how we can basically scale with the communication overhead, not scaling proportionally to the number of agents. And so we plan to look at mitigation of these communication bottlenecks and improving the algorithms. So one way also so this was basically looking at consensus algorithms. One way you can improve algorithms as well as through overlay networks. So you can basically set up an overlay in a way that you have faster communications. So in this particular work, which is led by Frank Capella out of Argonne, you can look at developing ring topologies that can improve the performance of the various protocols. In this case, he looked at using the gossip protocol as an evaluation of the different ring topologies. So the new algorithm, which is called diameter guided ring optimization, constructs these rings with minimal diameter, network diameter. It uses Q-learning for graph embedding to decide how to create the ring as it goes along. And in this particular case, the model was trained on 2000 epochs to be able to learn the particular policy of generating the rings. So I'm going to go quickly through that because I think I only have 15 minutes left in the presentation or so. But basically, so this shows you, we represent the state of a current graph topology, the latency information in the network, which typically is not taken into account when constructing ring topologies, and represented as an embedding of nodes in the network. And then at each step, the agent chooses a node based on the Q value. So agent 1 calculates the Q values for the network. It picks off the next job to connect to. These Q estimates allow you to estimate potential future rewards, so minimizing the network diameter. And then the reward function is based on the reduction of the network diameter based on this connection. So you can go and build the network as you go along. Obviously, for large networks, there's a scalability issue. So the team also developed an algorithm where you can partition the network into a number of pieces, and then each graph is constructed independently, and then you can connect the partitions. Obviously, here you might have to do some additional work to make sure that the solution is optimal. Another aspect of this work, which is very interesting, it also looks at the connectivity of a graph itself. So it looks if the network is too clustered or too sparse. So it uses this row value to be able to determine that. If it's close to 0, it means that the connections are relatively efficient in a clustered topology, but it might decide then to add a random ring to distribute this collection, so you avoid this clustering in a particular area. And then if it's closer to 1, then that means the graph is pretty sparse, and you might want to add the shortest ring that connects the nodes that are farthest apart in the network. And this is done basically looking at the various types of latencies in the system. So results from this part of the work, so they compared the different types of algorithms, so chord, nearest neighbor, Peregrine, rapid, and DGRO, which is ours. And this graph shows you the size of a network versus the diameter of a network. And consistently, you can see that DGRO performs better in terms of finding that shortest diameter. And this is obviously important because that means that protocols that are layered on top of this topology have quick communications between the nodes and thus can reach consensus faster. What is also interesting is that you can combine this ring construction with that's based on the latency in the network with existing algorithms that are built on ring topologies, so CORD and RAPID. And you can see that with adding this information to the existing algorithms also gives you better performance. So this is the network latencies that were sampled on Fabric, and with the size of a network and the diameter. And you can see that the graphs that have these dashed lines is a blue. You compare the full solid blue to the dash blue, and the green solid to the dash solid, and you can see improvements in the performance. Although you can still see that our solution just using DGRO gives you a better graph. And this is for a Bitcoin network evaluation as well, which shows similar results. So future work in this area is looking at exploring the scalability of the topology construction as the networks grow larger. We also want to evaluate this algorithm via emulation. So far the results that were shown in the previous slide were through direct simulation, but we can emulate them in a Fabric testbed as well. And also at this point, we want to combine the overlay topology construction here with a DGRO with the different consensus protocols that were showed in the prior section. So the other part of the problem is, so you reach consensus and the jobs are now sent to a particular facility for execution. So we want to look at how to schedule jobs within that facility. Ultimately, what we want to do is to be able to do it in a distributed fashion and taking into account resilience. However, we're starting with just simple job scheduling algorithms and looking at how swarm intelligence techniques can help or not help in this particular area, and how they can not only take into account performance, but also reliability of underlying resources. So in this scenario, we want to look at the problem as a job shop scheduling problem, where we want to minimize the execution of all the jobs. So we have the jobs J, and each of these jobs can, in addition, have a number of operations. So showing, for example, it could be depicting a pipeline within the workflow. And these operations may need specific machines for execution. So you want to be able to minimize the make span of across all the jobs that are being executed. And you have constraints for the problem. So each job must be processed in order of operations in the order. The operations of a job need to be processed in a particular order. And there's also another overlap constraint where the operations cannot happen on the same machine at the same time. So obviously this is an NP-hard problem. So we're using heuristics to approximate the solutions. And as I mentioned, we're exploring ant colony optimizations, which is a swarm type of optimization, swarm intelligence optimization technique that looks at scheduling these jobs and operations onto particular resources, so the order of execution. And so obviously the key concept there is that ants go through the system, they deposit pheromones on the path that they travel so that they can influence other ants going down these various paths. And the intensity of the pheromones that are being deposited guides the search and the paths to promising solutions. And then there is this trade-off between exploration, where ants explore different paths to potentially discover new solutions. But there's also exploitation, so using the paths that are more likely to follow the higher pheromones levels, which give you reinforcement on successful routes. So you need, in this solution, you need to balance the two. So this is the problem for formulation. So basically, you look at the various operations, and you put them in a disjunctive graph. In this case, you have the nodes represent the different jobs. So operations are the machine ID and the processing time for these operations. You have the conjunctive edges, which are the solid ones that show the precedence constraints, and the disjunctive edges that show you the resource constraints. So for this graph, using the N-colony optimization algorithm, you can find a feasible solution from the start to the end, to edge T. However, this is not necessarily an optimal solution. So we also can, once this feasible solution is found, we can subdivide the graph into various subgraphs and use traditional operational research algorithms to do a local search in this particular area and then integrate the solution. So obviously this is a very complex approach. We've been initially, we're getting very slow results in terms of just the ACO-based optimization. With the subgraphs, we're getting a little bit better results. This is still a test case on a very small case that you see here. So it's 6 jobs and 6 operations. The OR tools, which are the constraint programming with Satisfy solver, give you the optimal make span, which is 55 seconds, but it takes a short time to calculate that. The ACO technique itself doesn't give you an optimal make span, and it takes longer. If you do use local search, you get closer to the optimal make span, but again, the time is longer. However, if you scale up the problems, then we expect the OR tools will take longer to do the calculations, and the hope is that the ACO will perform better. And in addition, we plan to add reliability information in the to ACO, the reliability of the resources, which we hope will improve it will make these techniques to show better than the OR tools. So I mentioned the different techniques that we're applying, so different areas we're exploring. So the consensus algorithms, the network topologies, and the job scheduling. We want to be able, each of them has their own ways of evaluation through custom simulators or emulators, but we want to be able to evaluate these various components in a uniform way and the whole system as a whole. So we are developing a simulator that allows us to model the whole swarm environment and to account both for processing times, but also transmission delays. So because we're dealing with a distributed, geographically distributed environment, we want to make sure that the network is well represented within the simulator. So, and obviously we want to be able to test resilience and fault tolerance in this environment. So again, going back to our overall picture, we will have a dynamic pool where the users submit the jobs and workflows. We have now, in the simulator, we have different types of facilities, different resources, which have their own job pools, which are built by the agents that are selecting from the top level pool. We have a network that's represented as network between the different facilities, different computing sites. And we also have an inner network that represents basically the communications between the agents within a particular computational site. So we have local area networks, and we also have wide area networks. In the simulator that we're building, we have, right now we have implemented 3 different protocols for congestion control, so Reno and HiPEAC, and hypertext caching protocol, which also is one of the protocols that we can use for content sharing. We also have 2 active queue management algorithms. One does fair queuing and one does FIFO. And then we have various parameters that you can set in the simulation. So the simulation time, number of facilities, the NIC speed on the internal router, so these are within the facility, and queue length at these routers. We also have speed at the edge router, so communication between the facilities and the queue length there. We, in our simulation, so we have initial results where we have basically focusing on the network and doing just first come, first serve scheduling. to facilitate quicker experimentation, and we can build on that. So the agents just take jobs based on the availability of the resources. They share their workload information with each other. So this is a very simple consensus algorithm. So again, this is just to get the baseline simulation. And the agents basically pick the jobs that when they have the lowest workload for that at the particular time. So obviously they need to also update the dynamic pool. So they share, in this case, a common database that represents that pool. When the job arrives, it is added to the pool, and then it is available to all agents. And then once the agent takes a job, it makes it assigned, and when it completes, it makes it complete. So these are basically with that, you can look at different simulations. You can look at number of completed jobs and the average time for execution, the waiting time, turnaround, and others. And so you can look for these various scenarios and see which ones perform best. However, there's more work to do at the simulator level. So we want to be able to make sure that it's accurate in terms of simulating the network. So we plan to validate it against Fabric and also in the wild. So in summary, I talked about reimagining the workflow and resource management system, thinking about how we can distribute all the functions to build a system that will be ultimately more resilient. We are exploring various aspects of a problem, so the job selection, job scheduling, consensus algorithms, and overlay network. What we want to do is put it all together and look at the overall system performance. Although still a lot of work, I think interesting work can be done in these various areas, obviously. And we want to evaluate the approach using novel simulation methods and also by emulation in the Fabric testbed. One thing that of note to the project is that it requires expertise in a variety of areas. So as I mentioned, AI, resource management, networking, workflow management, mathematical modeling, resilience, all that put together to really think about an overall system that is basically redesigned from scratch. But I also think that this brings opportunities for collaboration. As I mentioned, we are now at the beginning of year 2 of this 5-year project, so there's a lot of opportunity to work together. Hopefully this gives you an idea of where we're heading. So right now, what we look at achieving is to exploring approaches to improving resilience, both by introducing reliability estimates in the job scheduling, also introducing failures in the simulator and the emulation environment, so we can look at how the current consensus algorithms and ring construction algorithms behave and job selection behave in this type of environment. As I mentioned, we need to calibrate the simulator against multiple systems. We also are actively working on using existing high throughput computing and high performance computing system logs to be able to drive the simulations and emulation. We need to test the system behavior under multiple failure conditions that occur in real world scenarios. And ultimately, we want to build a prototype of the system. So I'd like to thank you again for coming to this talk. I am open to questions and I'm more than open to collaborations. I think there's a lot of things that we can do together, and I'd love to explore that. Thank you.
Thank you very much, Eva. It's been a very wide project, a lot of things. It's really exciting. Very good. Congratulations. And we have a lot of interest from the audience. Usually from Europe, people is shy asking. So we have 5 questions for you. Okay, so first, Xavier Casas asking, well, first, thanks you for the great presentation. And he says, you have mentioned the use of machine learning algorithms for decision making. Have you investigated algorithms based on reinforcement learning so that agents can take decisions? Are simpler reinforcement learning algorithms enough, or do you think it's essential to have communication consensus between agents?
So that's a good question. And in part of our work, so the ring formation work that Frank Capello is leading is using Q-learning algorithms, which are reinforcement learning-based algorithms, to design the rings for communication. So that's one aspect of reinforcement learning that we're using. We haven't applied it into other places, but I think that's a very interesting direction and you know, definitely worth pursuing. I think, you know, what we've done so far in year one is build a foundation for exploration of different research paths and different opportunities. So I think we can, in some sense, the following years will be more interesting because we can do more, and we would love to collaborate with folks that have ideas of, you know, algorithms that we can use in our framework.
Very good. So next question from Sabri Plana. He asked, addressing the single point of failure issue with a multi-agent approach is intuitively appropriate. Are there swarm experimental or simulated results that demonstrate the improvement of systems resilience? Sorry. I don't know if you get it or I repeat, because
yeah,
you can read them if you want.
Yeah. I was so in the swarm intelligence community, there are lots of results that demonstrate that if a member of a swarm, you know, it disappears, or, you know, then it does, the system still continues to reach consensus and to have the general emergent behavior. So that's why we're trying to, that's why we think that this would be appropriate for workflow management systems. Here in our approach, though, we have, in our goal, we have, you know, the fact that the workload needs to be done. So performance is part of the issue, and also the fact that you don't want to have starve jobs from resources. So the latency of how fast things get scheduled also is part of a solution. So I think, you know, we'll see how that adapts and how it works. So it's, yeah.
Exactly. Eva was telling us that this is ongoing work still, no?
Yeah.
So we have another question from Benedict Riddle. How does this interact with the DOE leadership HPC facilities? Typically, they have restrictions in place to limit one access. Well.
Yes. So, okay, so this is a 5-year project. So I don't know, can we change DOE's mind in the next 4 years? But I don't know the answer. But there are, you know, some things that you can that are exposed, like the DTNs are exposed to the WAN. So at least the data movement can be orchestrated in that fashion. And also, if we prove that the techniques can be applicable to leadership class facilities, and we certainly have them in mind when we're talking about these solutions, then maybe the policies can be changed at the DOE facilities. I know it's a big. Yeah,
it's not only in the DOE facilities.
Yeah.
Everywhere we have the same.
Yeah.
Bueno.
But yeah, but you know, but it's also possible. I mean, I think realistically, if we look at the future of this work, I think what we'll find is that in some cases, the swarm intelligence is the appropriate mechanism for coordination of the resources. So if you're looking at IoT or edge type of devices, and then you can be a hybrid approach where you have a more centralized an entity that works at the HPC system level that can do the coordination. So that's my hypothesis, but we'll see if that's proven, you know, but it'll be interesting. Yeah.
Okay, then Raul Sirven, again, thanks you for the very interesting talk. Could you say more about how do you achieve dynamic agent deployment on the infrastructure?
Yes, so this is not an area that we explored right now, but I think you can. It depends on the infrastructure that you're using, but if you using edge devices, you can use Cube Edge to deploy the agents, for example. I don't know if that's the direction that you go into, but I think it depends on the infrastructure that you're running on and how you can deploy the agents.
Okay, great. Then we have one from Germán Molto. Thank you, Eva, for the very interesting talk. You showed how jobs may be distributed across multiple infrastructures in the computing continuum, in the edge, cloud, HPC, but jobs typically need to process data. How is data access managed to perform the data processing inside each job?
Right. So we have a model, and this is the same model that we have in Pegasus, where the data data transfer is represented as a particular node in a workflow. So if you have two jobs executing in two different resources, you have a workflow that has three jobs of a two execution and also the data transfer job in between. So the data transfer job, we imagine, will be also in this resource pool, and the network agent would pick up that job to do the data transfer, ultimately, create a path, provision a path between the two resources and do the data transfer. So that's an operation that we can see also fitting in well within this framework.
Yeah, sounds very reasonable. And we have a final question from Abdurrahsoul Ghazemi. Thank you so much. The swarm architecture seems to be top-down. The swarm in nature have bottom-up architecture. How could we consider this scheme in swarm?
Yes, so that you're right. So right now we have maybe top-down is the way I drew it, but you do see that the users are distributed across the different geographically. You can have the resources distributed geographically. The point of connection is this central work job pool that you have at the top of the picture, right? So but in reality, this is a distributed infrastructure that's layered on the bottom of a network as well. So you can imagine that users submit things to the local storage or to the local job pool, and from there it propagates to the global job pool. So right now we don't do this scenario. This is something that would be the mechanism to build up the global view of the system, of a global job pool, but you can imagine that you have a local submission, and then that's integrated into the global view, and that would be the more bottom-up swarm way of looking at it.
Very good. Well, with this, I have a final question from my side. At the beginning, you mentioned between the challenges, one that for me is one of the more difficult, debugging in a distributed environment. Have you thought about how to debug the workflows in such environments?
Yes, I think, yeah, I think you're right. That's a challenge. I think, part of it is that we try to use swarm intelligence to do a lot of take away some of the necessity from debugging to do the self-monitoring and self-healing. Take advantage of these aspects. Also the fact that you have this dynamic reliability in the sense that agents can take over actions for other agents. So again, kind of reducing the need for low-level debugging. Truthfully, I think, as AI becomes better, I think a lot of debugging can be pushed into the AI space to, for LLMs to look at execution logs and be able to interpret them, using maybe reinforcement learning techniques to do some of the training, or, so I think I'm hoping that, by the time we're done with this project, it's not going to be a huge issue in terms of, or at least that I think we'll make progress on the debugging part with AI-assisted debugging.
Okay, very interesting. Molt bé. So with this, I'd like to close the webinar. And with this, I would like to thank everybody, especially Eva, for giving such a great talk, and all the attendees for listening to it.
Thank you so much. And if you're at
Thank you, Eva.
Supercomputing, love to see you guys. So thank you.
Exactly.
Thank you so much. Bye-bye.
Okay.